We're now going to consider different types of collisions. So we've seen that when two objects collide, some different things can happen. So for example, we could have something like this, or we could have something like this, where the two objects move off together. So one way to classify collisions is as elastic or inelastic. Inelastic collisions are typical of everyday collisions. In inelastic collisions, some of the kinetic energy is lost. So it's typically lost in the form of sound energy or heat energy. If two cars collide, there's a lot of sound, and some of the energy also goes into the crumpling and deforming of the metal from which the cars have been built. So an inelastic collision is one in which kinetic energy is not conserved. So in the collision, the linear momentum is conserved as long as no external forces act, which is the condition that we're considering for our collisions. Now, in the case where the two objects stick together after the collision, this has a special name. It's called a perfectly inelastic collision. So for a normal inelastic collision, the conservation of momentum holds. So we can say m1u1 plus m2 U2 is equal to m1v1 plus m2v2. In this perfectly inelastic collision, after the collision, the two bodies have the same speed. So we can say v1 is equal to v2 is equal to v. So we can derive an expression for v for the case exactly like this, where initially one of the bodies is moving and the other is stationary. So we'll let body 2 be the stationary body, so u2 is equal to 0. So in this case we have m1u1 is equal to m1v plus m2v. So we can pull v out as a common factor, so this is equal to m1 plus m2 all times v. So our final velocity v is equal to m1u1 divided by m1 plus m2. Now there's a really nice demonstration where we can use this equation to work out the initial speed of the object. So this demonstration is of a ballistic pendulum. So in this case I've got a bullet which is loaded here. I've pulled this spring back, so at the moment there's a lot of potential energy stored in that spring, which I'm going to release very soon. That's going to give the bullet some initial velocity. The bullet will then shoot into this block of paraffin here and hopefully become embedded in it. So during that collision, the momentum is conserved. The initial momentum of the bullet goes into the final momentum of the bullet plus the paraffin. At that point, the paraffin block with the bullet in it begins to move, and it continues to move up until all its kinetic energy has been converted into potential energy. So we can use the height it moves to calculate the amount of kinetic energy it initially had, and then we can go back from that kinetic energy it initially had. We can calculate how much speed the bullet had when it was launched into the paraffin block. So in this case, my bullet has a mass of 7.7 grams, my paraffin block has a mass of 76.4 grams, and the length of the string from the pivot point up here to the center of mass of the paraffin block is 22.5 centimeters. So we'll be using those numbers later to do our calculation. But let's have a look at this demonstration. Okay, so we can see that it rose to an angle of, just let me jump around here, it rose to an angle of 34 degrees. So we can see it rose to an angle of 34 degrees, so we can use that to perform our calculation now.
So we're considering our ballistic pendulum. So initially we've got the paraffin block and we'll let it have mass MP here, and we've got the bullet travelling towards it with some initial speed UB, and we'll say that the mass of the bullet is given by MB. So as the bullet collides with the paraffin, assume momentum is conserved. So momentum will be conserved, linear momentum will be conserved if external forces aren't playing a significant role in this, and they're not. We've got the gravitational force acting on the system, but that is very small compared to all of the internal forces involved. So then the bullet becomes stuck in the paraffin block, and the paraffin block moves up. So eventually it moves up to some height. Let's call that h, where it comes to rest. And from when it starts moving to when it comes to rest, we can assume that mechanical energy is conserved. So we've basically got kinetic energy being converted into potential energy. Okay, so let's write down the equation to describe this first step. We've said that the momentum is conserved. So the initial momentum, the paraffin is stationary, so the momentum is all in the bullet. So the initial momentum is given by the mass of the bullet times the speed of the bullet, and this is equal to the final speed of the bullet plus the paraffin. So mass of bullet plus mass of paraffin times the final speed. So this gives us the speed just after that bullet has embedded itself in the paraffin. And now we consider the second part, where they're now moving together as one object and energy is conserved. So here we've got that the initial kinetic energy, which is a half mass of the bullet plus the mass of the paraffin, times v squared, which was the speed we just calculated here. And then at the end, we've got all the energy in the form of potential energy. So this is the mass of the bullet plus the mass of the paraffin times g times h. So now, if we let L be the length of our piece of string from the pivot point to the center of mass, that's L, then along here, we've got the same L here. And this is the theta here that we've measured. So this length here is equal to L cos theta. And so this length plus this length here is L. So this tells us that the height h is equal to L minus L cos theta. So we'll be able to use that for the h here. But what we can see is this will cancel off nicely. So we've got v squared is equal to 2gh, just rearranging this second equation here. And what we're trying to find is the initial speed of the bullet. So we want to find ub. Okay, so let's call this one equation A, and we'll call this one equation B. So equation A, we can rearrange and we can write, well, ub is equal to mb plus mp over mb times v. And then in equation B, we've worked out what v squared is, so we can just substitute in the square root of that for v. So this is equal to mb plus mp over mb times the square root of 2gh. So that was sub in B. Okay, so now we can actually evaluate this because we measured all these things. So the mass of the bullet was 7.7 grams. The mass of the paraffin was 76.4 grams, so that's in grams. The mass of the bullet was 7.7 grams. So we've got grams on the top and grams on the bottom. So the units cancel each other out. So we don't need to worry about converting this into kilograms. You can if you want, you won't get it wrong, but we can save ourselves some time. And then we times it by the square root of 2 times gravity, which is 9.80 times h. And for h, we were using L minus L cos theta. So this is L minus L cos theta, which we can pull L out in the front, and it's L1 minus cos theta. So this is times L, which was, we measured it, L was equal to 22.5 centimeters. So this is 0.225 meters. We do need to be in SI units here because we're not dividing by an L. And then we multiply it by 1 minus cos theta, and we measured theta to be 34 degrees. So we can substitute this into the calculator, and we end up with 9.48 meters per second. We should just give it to 2 significant figures because a lot of the data was only measured to 2 significant figures. So this is 9.5 meters per second as the initial speed of the bullet as it embedded itself in the paraffin.